For this problem, we're going to solve a system of linear equations in three variables using substitution or elimination. We have the system x minus y plus 2z equals 5, 3x plus 4y minus z equals negative 2, 5x plus 2y plus 3z equals 8. I'm going to solve this using the method of elimination. We number our equations. We'll call this equation 1, this is equation 2, this is equation 3. First thing we want to do is eliminate the variable y from the second and third equations. We're going to use our first equation to do that. To eliminate the variable y from the second equation, we're going to first multiply equation 1 by 4. So we'll have 4x minus 4y plus 8z equals 20. We're going to rewrite our second equation here, 3x plus 4y minus z equals negative 2. Now to get rid of the y variable, we're going to add these two equations together. 4x plus 3x is 7x, negative 4y plus 4y is 0, and then 8z plus a negative z is going to give us plus 7z. And then 20 plus negative 2 is 18. This will be our new equation 2. Now we're going to eliminate the variable y from the third equation. To eliminate the variable y from the third equation, we still want to use our first equation. We're going to multiply our first equation by 2. So we'll have 2x minus 2y plus 4z equals 10. And we want to rewrite our third equation, 5x plus 2y plus 3z equals 8. To eliminate the variable y, we need to add those two equations together. 2x plus 5x is 7x. Negative 2y plus 2y is 0. 4z plus 3z is 7z. And then 10 plus 8 is 18. We're going to call that our new equation 3. We're going to work with, or let's rewrite our system first. We keep our original equation, x minus y plus 2z equals 5. Rewrite our second equation now, I'm calling this 7x plus 7z equals 18. And then we have our third equation is 7x plus 7z equals 18. At this point, if we see these last two equations are identical, so we have a redundant equation. Because we have three equations and three unknowns, but one of these equations is redundant, it's really like we only have these two equations and three unknowns. So our system will have an infinite number of solutions. We're going to determine the infinite number of solutions by solving this second equation for x and get it in terms of z. So we're going to have 7x plus 7z equals 18. 7x equals negative 7z plus 18. We're going to divide both sides by 7, so we'll have x is equal to a negative z plus 18 sevenths. We've expressed x in terms of z. Now we need to get y in terms of z to complete our solution. Here we've rewritten our first equation, and here we have x solved in terms of z. So we're going to take our definition for x now, we're going to plug that into our first equation, and then solve this equation for y to get it in terms of z. So here we would have negative z plus 18 sevenths, that's what x is, minus y plus 2z equals 5. So we can use our grouping symbols, negative z plus 18 sevenths minus y plus 2z equals 5. You can collect like terms here and bring this 18 sevenths to the other side. So we'll have negative y, negative z plus 2z is plus z, equals, then 5 minus 18 sevenths. We'll have negative y. We want to bring the z to the other side, so we'll have negative z. And 5 is really 35 over 7, so 35 minus 18 is 17, so we'll have plus 17 over 7. And we need to get rid of this negative, so we'll multiply both sides by negative 1. So y is equal to z minus 17 over 7. So now that we've expressed x in terms of z and y in terms of z, we can write a general ordered triple as our solution. X is negative z plus 18/7. Y is z minus 17 over 7. And then z is just z. We'll say z is any real number. And we have our ordered triple solution.